Hi, I'm Antonio Sala, and in this video we will recap the basic idea of modeling of a 3-mass and 4-spring system, and we will write the normalized state space equations in matrix form. This is the sketch of the physical system to be modeled, and in a companion video we in fact explain with greater depth the modeling of each of the equations. So you are referred to said video to complement the ideas. We'll have it here. Perhaps you should view that video before viewing this one. So we have 3 masses, 4 springs, 1, 2, 3, 4. We have some friction in the wheels, and the origin is the black fixed wall at the left of this sketch. Positive will be movement in the right-hand side direction. So, if Ln denotes spring natural length, the force of the springs will be its length, difference in positions minus the natural length, times a given spring constant. And if you pause the video and look here and here, you must be able to derive these equations. As I said, if you don't understand what we are doing here, you should view the companion video. So once we have this system, we may compute, if so wished, the equilibrium point when everything is constant, including, of course, the input, u. So equilibrium will be if we keep this thing at a fixed position, because the input are the displacements of the right end here. So if we keep it at a fixed position, friction will make things stop at an equilibrium position given by, when everything is constant, derivatives of constants are 0. So if we replace derivatives with 0, we get the equilibrium equations. So solving these 6 equations will give me the so-called equilibrium point. Of course, there are many letters here. So in an actual engineering problem, I need to know everything except 6 of these letters. So usually, if I know the spring constants and the natural length and the input variable, the arbitrary position in which I am fixing this right end, well, then I can compute the 6 positions and speeds in equilibrium. For instance, when everything is stopped and positions are constants, speeds are 0. This is what this equation says, but okay, we expected it intuitively. And apart from 0 speeds, if I then think in these equations with, of course, 0 equilibrium speeds, then I can obtain the equilibrium positions if the input is assumed known. However, in many engineering problems, I don't really care about the equilibrium, or well, I do care, but in an earlier design phase, when I select the springs and how to build this system. But in actual use, for instance, this may be vibrating because it's attached to something else, and I wish to understand the vibrations of these masses. So vibrations means displacements around its equilibrium point. Then if this is my actual engineering problem, displacements, vibrations around the equilibrium points, then I don't actually care on what the actual equilibrium is, in the sense that if I assume incremental variables in linearization, then natural lengths have no increments, they are constants, so constants disappear in the linearization, in the incremental variable reference system, so they disappear. And if I change from capital P, indicating the positions measured from this point, to lowercase p, indicating the incremental positions from the equilibrium, then changing to lowercase just yields these equations. Again, I let you derive it by looking at these equations, pausing the video, so you will get this equation, which is the linearized model around the equilibrium. And now in these equations, the equilibrium point of these incremental coordinates is 0, and it actually refers to the equilibrium positions of this thing, whatever it is. in the sense that I will never be able to compute what is the actual equilibrium point of the original absolute system, because in here, when the increment of u is 0, the equilibrium point of this will always be 0. Okay, that is what we wish. If everything is in equilibrium, nothing moves from equilibrium, so all the increment variables are 0. And when I move a little bit the input, then everything will start vibrating. We'll simulate it later. In fact, for simplicity, we will simulate with all the spring constants being equal. So we will see plots of the time response of this system, in which all spring constants, instead of k1 plus k2, I just wrote 2k. Okay, so again, if you carefully look here and here, you will see what I mean. So in order to simulate this system in MATLAB, we may wish to write it in so-called normalized matrix form, which is this one. Why do we actually want to write it like this? Well, because linear systems are very frequently used in engineering, then there are many toolboxes in which I just write constant matrices A and B, and the software sets up the differential equations and whatever. And in fact, even theoretical computations on the eigenvalues and exponentials of these matrices, etc., are popular in many textbooks. So it's of great interest to write my equations like this. Writing a linear system of equations in matrix form is something that you do even in high school, maybe. So by looking at these equations, for convenience, I am fixing them on screen on the top left. Then, for instance, starting with the easy part, B matrix is made with the coefficients that multiply the input u. So as input u only appears here in this equation, and it's actually multiplied by k divided by m, then this thing is here. So we have that u appears in all equations multiplied by 0. It does not appear at all, except in the last one, in which it is multiplied by k over m. So we write it here. Then matrix A must be built by extracting the coefficients that multiply positions and velocities, because the state vector x, must be built with the things that appear as derivatives in the left-hand side of my equations in normalized form. So this thing is this thing here, and this is the state vector x, which is built by vertically stacking position, velocity, position, velocity, position, velocity, 1, 2, 3. Good. So once we have the state vector, which are the coefficients that multiply these variables? Well, first equation, derivative of p1 equal v1, means that the derivative of p1 is here, and v1 is just, if we recall the matrix product, 0 times p1, this 1 is multiplied by v1, this 0 is multiplied by p2, etc. So 1 times v1 is what we find here. Now, second equation, acceleration of mass 1. Well, that second equation, if we extract coefficients, we'll see. P1 in here, it's multiplied by minus 2k divided by m. So this thing in the matrix product will be multiplied by P1. So that's why this factor building that coefficient. Now, speed 1 is multiplied by minus b over m. So this minus b over m is what will be multiplied by v1 in the matrix product. So this translates to this. And last, p2 is multiplied by k over m. So this k over m is indeed what will multiply p2 when we carry out the matrix product. And of course, these three zeros will multiply these three variables, so v2, p3, v3 will not appear in the equation, and indeed they do not appear in here. Good, so we finish with the second equation, and then third equation, the derivative of P2 is just 1 times V2 and 0 times the rest of state variables, and this one multiplies the fourth state variable here, so this one encodes this equation here. In a totally analogous way, you can quickly see, I leave it to you, that the fourth row of A encodes the fourth state equations of my model. Minus B over M speed, minus 2k over M times the position, this by this, and so on. And again, I let you pause the video and realize that these two equations correspond to the last rows of the matrices. So this Ku appeared here, and the rest of the coefficients in here will end up in the corresponding row of A. So as I said, you can pause the video and do it by yourself. So with this, we'll have the matrix representation of the state equation in here. Normalized representations also have what's called output equations, y equals Cx plus du. So what's the output? Well, it depends on each application. I might be interested on the vibrations of mass 1, on the force of a spring 4, or whatever. So for instance, if I am interested in all the positions and speeds, then in my particular applications with that interest, the whole state vector, 6 things here, will be my output. Then in that case, I would type somewhere in MATLAB C as the identity matrix and D as 0, so that this will disappear and I will get this equation. But as I say, C and D are problem dependent because physics is encoded here, the dynamics, how things change with time, and then which of these 6 variables or combinations of them are of particular interest in my engineering problem is up to my choice. So A and B will be the same for every use of this spring system, but C and D may change. So we'll conclude with this. We'll have this normalized representation, and we may write some C and D for my particular problem. These matrices A, B, C, D are used in theoretical developments and in linear system simulation software. But of course, this linear system will always have this equilibrium point, 0, because we are not interested in the actual positions, distance to this black wall of the masses, but only in the small vibrations around its equilibrium when this thing vibrates. So if this is our problem, then we can simplify these equations with lateral lengths and forget them and end up having this set of equations, which, in order to use linear system simulation software or linear system theory, can be written in matrix form, as we did in this slide. Actual simulations will be carried out in a forthcoming video, but for the moment being, we end here. Thanks for watching.